И запись. Ну, запись. Да, не надо. Вот, вроде все работает.
Ура, спасибо. Да, естественно. Спасибо большое. Я прошу прощения. Ага. Отлично. Ну, поехали. Oh, sorry. Let's start. So last time we almost proved our big theorem, namely there are affine algebraic varieties and there are unital commutative finitely generated K algebras without nilpotence. These are the same, that's what we're aiming to prove, but last time we constructed such a functor, so algebra A goes to the maximal spectrum of A. Okay, and in the opposite direction, affine algebraic variety Y goes to the ring of global regular functions on Y. Okay, so that's what we constructed last time, and we proved that there's a natural sort of evaluation morphism from A to the algebra of global regular functions on the spectrum of A, and last time we proved that it's an isomorphism. Oh, sorry, yeah. Here, yes, thanks. Oh, thanks. Yes, thank you. This is what I proved, but maybe somebody still remembers the definition of affine algebraic varieties. There was the key property that for any variety x, if we have a morphism pi from x to our would be affine algebraic variety spec A, then it induces the map in the opposite direction pi star, pull back from the regular functions on this spectrum, and we know that this is already A, took the global functions on X. Okay? But by definition, for the affine algebraic variety like this, this should be a bijection. Okay, so this should be a bijection between morphisms of algebraic varieties from X to spectrum of A, and the morphisms of algebras, of K algebras, from A to global functions on X. Okay, so this we have to check. We have constructed certain topological space, the spectrum of A with Zariski topology. and the sheaf of regular functions, but now I have to check this main property. Okay, and this is all that remains to check. Okay, so let's do this. First of all, let me check that this map from pi to the pullback on functions is injective. So it does not, the different morphisms go to different algebra maps. So in other words, pi is uniquely determined by pi star. Okay, so how do we do this? Just pi is some morphism of algebraic varieties, but it is certainly, if you remember, determined by the map of underlying topological spaces or just sets. Okay, so we have just to check that it works on the level of sets. Okay. Okay. Now, given a point here, we have to determine what is the corresponding point here. But how do we determine this point if we know pi star? And what are the points of spectrum of A anyway? Does anybody remember?
It's algebraic morphisms.
Yes. So we want to construct pi of x is an algebra homomorphism from A to K, and just evaluation at the point pi of x. Okay, so how do we reconstruct this point given the pullback on functions? So we know the pullback on functions from A to regular functions global on x, and how do we reconstruct pi of x? Okay. Right, absolutely. So evaluation at the point pi of x is just the composition of two. We take pi star and then take evaluation at the point x. Right? There we are. So given this pullback on functions, we reconstruct just set theoretically the image of x, of small x, right? Okay. So this is done. The injectivity is proved because we reconstructed the set theoretically this morphism from x to spectrum of A just by the pullback on functions. Okay. So now we have to prove surjectivity. Of pi star. So in other words, given any algebra morphism from A to regular function of x, we must construct the corresponding morphism on the level of underlying varieties. So we are given, say, phi from a to regular functions on x and want to construct pi such that phi is equal to pi star. So how do we construct pi? Again, set theoretically.
Again, use this formula.
Just by this formula, right? So just use the same formula for pi set theoretically. And check that pi is continuous and a morphism of algebraic varieties. Well, and yes?
What is evaluation at p of x? It's an evaluation of what?
It's a map from A to K. Yeah, this is evaluation at pi of x is a map from A to our base field. Was it your question or?
It's an evaluation of homomorphism, so it's just an p of x as a map, yes? Because p of x is a map itself.
Pi of x is a point of the spectrum of A, right?
Yes. So you just use it as a...
And any point of a spectrum is a homomorphism like this. So we produce a homomorphism like this, just as composition. We pull back to x, and there we evaluate at point x.
So this is different evaluations. On x, it's an evaluation at point, and on p of x, it's an
Also evaluation, but
using homomorphism as map.
I don't understand your question. So given any point of any variety, then you have evaluation at this point, a homomorphism from regular functions on this variety to the base field. Yeah, that's our notation from the last time.
Мне кажется, Антон имеет в виду, что, что сама точка есть геоморфизм по определению.
Yeah, for a spectrum, for a maximal spectrum of ring, all the points by definition are such evaluation homomorphisms.
So when we are finding p of x, it's the same as finding evaluation at it.
Yeah, just tautological. Somehow I missed the point of your question. I'm sorry.
Можно сказать, что evaluation px
Yes.
это px.
Yes, in a sense, yes.
Not by evaluation at x we can't see this because it's
No, for example, x could be some non-affine algebraic variety, like projected space. So, for arbitrary variety, there is no such bijection, but for affine there is.
Точки в x, поэтому точка x однозначно определяет evaluation.
Oh yes. Yes. Yes.
Тебе не нужно, чтобы у тебя точки соответствовали максимальным идеалам для x.
У нас есть x и стало x.
Okay.
Правильно, для эффективности мы просто говорим, что наше π это вот наш evaluation от x на φ.
Yes. Then I have to check that it gives rise to a continuous map, and that it's a really morphism of algebraic varieties, so that the induced map on functions is a map of sheaves, but that's routine check, so to say. Okay, so this big theorem is proved, and in particular we see that there is such a sort of bijection, but more intelligent way of saying this is that this is an anti-equivalence of categories algebraic varieties and just algebras. But with opposition, right? Because if your algebras map in one direction, yes, affine algebraic varieties. Thank you. Affine algebraic varieties and okay, algebras, but I mean unital, finely generated, commutative, without nilpotents, just as here. Okay. And now we already had this notion, but maybe let me say it once again, that an algebraic variety is a ringed topological space ringed with a sheaf of regular functions such that it has a finite cover by affine varieties. So topological space ringed with a sheaf of regular functions admitting a finite cover with affine algebraic varieties. Okay. Yes, for example, P1. Yes.
Прямая с двойной точкой подходит в это?
Yes. So far, yes. It's called raviolo. And it is also, so P1 is glued from two copies of the affine line. But the corresponding intersection is just A1 without 0, and if here we have coordinate x and here coordinate t, then x is t inverse. Okay, that's you all proved in the first home assignment. But the ravioli is also glued from two copies of A1, and they are again glued over the punctured affine line, but here x just equals t, surprisingly. So there are two 0 points. Here is x equals 0, here t equals 0. But they are different points. It's called inseparable algebraic variety. Okay, and it's not affine. This is not affine, and this is not affine. But we will speak more about this. So far, it looks like some ugly thing. Okay. So our main topic for today will be again another proof of Nullstellensatz. But before, let's say a few words about construction of new algebraic varieties. Yes.
Cover should not be open. Yes. Can be not open.
Finite open cover. Yes.
But how can be open set that contains x but not contains t?
Well, this is an open set, a affine line. This is the upper affine line. There is another lower affine line, and they coincide almost everywhere except for 0. Inseparable, yeah, algebraic variety. Fine. of algebraic varieties. So we'll return to this topic a few times in the future. For example, there is an important construction of the product, like this. For example, A1 times A1. But this is, in fact, a rather non-trivial construction because, for example, as you saw in your homework, the Zariski topology here is not the product topology there. So it's a non-trivial construction. And we will not speak about it anymore right now, but instead we will speak about subvarieties. So if I have a variety X, and a subset inside, I can equip it with the induced topology. On Y, and an induced sheaf of regular functions. So in scientific terms, you had the sheaf O sub X here, then we just define the sheaf of functions on I as a restriction. Like this, and so we'll speak more about sheaves and operations on sheaves, but now let me say that by definition OY of, say, Z, where Z is an open subset in Y, is the set of locally defined functions in the neighborhood of Y. So what does it mean? We take an open cover U I, so the union of UI, and those are open sets in X. But this union contains Z. Okay, and then UI intersect Z by construction of this induced topology is an open in Z. Okay, so I need some functions Fi on UI, so regular functions of X of UI, such that the restriction Fi onto UI intersect Uj intersect Z equals restriction of J to UI intersect Uj intersect Z. Okay, and then they all glue to some function in here. Okay, so these are the collections UI, Fi, like there. In X, yes. No, they cover Z. Like, well, your X is everything, your Z is like this, and we have to cover it by some open sets inside X. Okay. Here? Yes, it is a requirement. We take some functions on those open subsets of Z that glue on Z, but that are restrictions of global functions on X.
Если f-то, они все-таки лежат в пучке у x.
Yes, but we're only interested in their restrictions to Y.
Априори выполняется.
So we consider such functions on Y that come from regular functions on X. That's a requirement, but they glue on Y. They do not necessarily glue on X. Yeah, so they match here, but they do not have to match necessarily there.
То есть на опыте они могут быть отличаться от опыта.
When you are writing open in Z, maybe you mean open in
This intersection is open in Z.
Do we need it to be open in?
Just the definition of induced topology. Yeah, the topology of Y is induced from the ambient space X. So the functions must be restrictions of some regular functions on X, but they have local behavior. So they must be glued from some functions on open cover on Y. Okay. So absolutely arbitrary. So this way we obtain some ringed space, but it will not be good in general. Yeah, for example, if we consider some arbitrary subset of complex numbers, then with this induced structure, it will not be algebraic variety or anything like this. But sometimes it will. So now the theorem we are going to prove. Yes?
When we find the regular function on Z, we don't care about what is Y. It's okay, yes?
But Z is an open subset of Y.
Yes, but so functions depends only on the set.
Only on Z itself, yes, that's true.
Okay.
Yes. Okay. So if X is an algebraic variety, and Y in X is locally closed. Yes. UI arbitrary open. So if you take a locally closed subvariety, subset. Then yes, thank you. Then Y with the induced structure is again an algebraic variety. Okay, and maybe this is part 1, and part 2 is if X is affine and Y in X is closed, then Y is also affine. Okay, so let's prove this. And since all our definitions are in a sense local, then the check of 1 boils down to the check for the case when x is affine. Okay.
Сейчас, а можно
Yes.
локальная замкнутость это
Yes, I will say in a moment. Okay, so then locally closed means an intersection of closed and open. Means that y is the intersection of z and u. So this is closed in x and this is open in x. Okay, that's the definition of locally closed. So then clearly it's enough to prove this separately for closed and for open subspaces. Prove for x equals spectrum of some algebra A and Z closed. Closed in Zariski topology, so this means that Z is the zero set of some ideal J. Okay, and then, well, this J is in fact the set of all F in A such that F restricted to Z equals 0. Okay, so in particular this ideal is a radical ideal and the quotient A modulo J is a ring without, is an algebra without nilpotence, and we can take its spectrum. Arbitrary closed subset of our affine algebraic variety spectrum of A.
Which is in future will be Z
from here, yes. So
intersection. But why we say that our G is equal to radical of G? It's not evident.
It is because I consider all the functions whose restriction to Z is 0. No, not that. This is just tautology. Because they are functions. Yes. So if f to some power vanishes on Z, then f necessarily also must vanish on Z. Nothing deep in this. Because in this definition, this ideal is radical ideal.
Excuse me, but
yes.
You first defined Z. With you.
I started.
Then you said inversely, if we have some Z and it is closed, then define G as the number of functions that vanish on it, and then it's radical. So it's two statements, two different statements in different directions. Because
well,
you can
I have trouble counting.
It's not radical, and it will define a closed subset. G.
Yeah, it's possible, but I take some particular J. Yeah, namely the ideal of all functions vanishing on this closed subset.
I mean that if you first introduce some j, then you just say that you take radical of j that was previously.
Okay, maybe I can start with something, and then this j will be the radical of j prime. Okay. Anyway, this is no nilpotence, so maybe let's call it B, and then I claim that Z with induced structure. Well, all questions to Sasha Gonzalez. I take a closed subset in the maximal spectrum of some algebra. Then by the very definition, when I say that's a closed subset, it's the zero set of some ideal. Namely, there is one best of all ideals with such property. This is the ideal of all functions vanishing on Z. And this is a radical ideal. I can start with any other ideal defining Z, and then its radical will be that. Okay? So now I claim that this closed subset with its induced structure of a ringed space will be just spectrum of B. And again, this is a routine check, and I will skip it. But it's really very simple and straightforward. Now, pardon me?
Не очень понятно, почему мы можем считать, что у нас не локально
No. This was just maybe part A of my argument. So any locally closed subset is an intersection of a closed and an open subsets. So I will first consider the case of closed subsets, and now I will consider the case of open subsets. Okay? Now, if I prove my theorem separately for closed subsets of affine varieties and for open subsets of affine varieties, then I'll be done. Because the part one is local in its formulation, and all the definitions are local. So I have to check it locally. Okay? And locally, everything is glued from affine varieties. So it's enough to check it for X affine.
Why, if we proved this for two sets, we proved this for intersection? It's not obvious.
Because I first prove that any closed is also a fine algebraic variety. Okay? As I've already proved. And now I take its open subset. That's what I'm going to prove now. So I do it just in two steps.
То есть на пересечение замкнутого и открытого все-таки не открыто.
It will be open in Z. It will open in Z. I already proved that Z is an affine algebraic variety. So now I have to prove that if I take an open subset in X, then yes.
Вот мы хотим, чтобы в итоге Z было покрыто конечным числом афин.
Yes, but it is already
Что локально покрыто конечным афин, почему глобально будет тоже конечное число?
Because X itself is covered by finitely many open affine varieties, and now in each of those, yeah. So this is my X1, X2, X3, and inside I have Z1, Z2, Z3, and for each of them I know that it's a fine algebraic variety, and there are three of them, so they cover the whole Z. Okay. So now I have to check for open subsets of affine algebraic varieties. Okay. Now, since it's open, it is by your last home assignment the union of basic open sets. And we are almost done. The only problem is that this union is really finite. So we have to check that we may choose a finite subcover. Pardon me?
Everything is not trivial.
Yeah, but we don't know this word yet. So only.
From quasi-compactness.
Right, absolutely. Have to check that any open subset of an affine algebraic variety is quasi-compact. So any open cover has a finite subcover. And we will do this maybe later today or next time. At least we have to start with something, like with Hilbert basis theorem. Yeah, at least for a fine space. Okay. So part 2 is also proved, yeah, right here, and simultaneously we also proved that the global functions on x surject onto global regular functions on y. Okay, just because this algebra of functions was the quotient of functions on the ambient variety x. Okay, so we are done with this. So once again, what is the bottom line? Yes?
А как вот возьмем теперь спектр этого U, и это будет...
No, you can't take a spectrum because it's not necessarily affine. For example, you can consider like the plane without the origin, and it's an open subset in the plane itself. This is affine, but it's not affine. We'll see this in more detail later on. But for example, the regular functions on this punctured affine plane is what? How do you think? Yeah. No. Just polynomials in two variables. So the restriction of functions from the plane to punctured plane is an isomorphism. Yeah, and so this cannot be affine. Otherwise, it would be isomorphic to A2 by our big theorem. Because affine varieties are the same as rings of global functions. So here the ring of global function is the same. It's sort of Hartog's theorem, yeah, if you studied complex analysis. Pardon me? Yeah, and that's it. We don't need anything else by definition. Yeah, by definition, a variety, algebraic variety, is something that is covered by affine algebraic varieties. These are all affine algebraic varieties. Right, because there are spectra of localizations, and the only thing to check is that this covering is finite, and this we deferred till later on. Yes.
Why it is not affine? We said that the global sections are the same.
Yeah, because we know that this is affine.
Yes.
And we know that there is our famous anti-equivalence of categories between algebras and affine algebraic varieties. Now, this is the same as here, so.
And why have we these rejections? this surjection?
Just by this construction, because our B is the quotient of A, so A surjects onto B. Okay, so the bottom line, once again, is that we can always restrict to subsets, but if we restrict to random subsets, we get nothing good. But if our subsets are locally closed, then we stay inside the category of algebraic varieties. Okay, so the locally closed subset with induced structure is an algebraic variety. Okay, so now let's go back to the basics, to the commutative algebra, and as I said the very first class, our algebraic varieties are covered by affine algebraic varieties, so they play a role of the open balls that cover the usual manifolds in differential geometry. And now, for the rest of today, we'll study the local properties, like the properties of those basic open subsets. So this is sort of analog of first or second year analysis. Okay, the local properties of spectra of algebras are the same as local properties of open sets in differential geometry. So here they're studied by the usual analysis as opposed to manifolds. Now these are studied by commutative algebra. Okay, so pardon me. It was just this. This part A was just literally part 2 of the theorem. Okay, so our algebraic geometry is an analog of differential geometry, and today we'll do the commutative algebra, which is an analog of analysis. So I will give another proof of Nullstellensatz, and to begin with, we will need a lemma of M.Noether.
Можно вопрос?
Yes.
Вот мы там утверждали, что DF афинно, правильно? Вот, правильно?
Oh yes, certainly.
Это не совсем очевидно.
But that was proved in your second home assignment, I hope. Didn't you prove it?
Наше значение было чуть другое, но эквивалентное этому.
The DF is the spectrum of the localization, yeah, like this. So it's affine by definition.
Какой должен быть идеал, чтобы вот DI должен быть, чтобы было афинным?
В смысле, это элемент алгебры.
Да, если я хочу проверить, является ли афинным D от какого-то идеала.
So even if you dispose of zero sets of some ideal, yeah, then it rather be the principal ideal, I think. Yeah. Okay. So what is M.Noether lemma? We have a function, a polynomial function. And the degree of this f is d. So I mean, it may have. It's not necessarily homogeneous. Yeah, it's of degree d and possibly less. Then there is a coordinate system y1 and so on, yn. So so it's just a linear change of coordinates from x. Okay, such that f is a monic polynomial in the last coordinate. So f is equal to y to the power d plus y to the power d minus 1 times some p d minus 1 in y1 and so on. Yn minus 1 plus yn to the power d minus 2 pd minus 2 in y1, so yn minus 1 plus so on. Okay, but the leading coefficient is just 1. Pardon me?
Чтобы... ну да,
yeah, because we just made a linear change of coordinates and the degree was d. So there is a point. Pardon me?
The monic in Yn.
Monic in y. Sorry, in y. Yes, thank you. Okay. Yeah. So there is. So maybe let's write down f is the sum of fd plus f less than d. So this is homogeneous of degree d. And this is degree less than d. Okay. Now fd is not 0, and hence there is a point a in our affine space such that fd of a is not 0. Say is 1 maybe. Up to rescaling fd of a is just 1. Fine. And now let's take a coordinate system. So this is y coordinates are chosen such that the point A is just 0, 0, 0, 1. Okay? So we have a big freedom of choice. We choose any coordinates with only requirement that our point has such a coordinate. It's okay. And then then necessarily fd of a fd of y is monic in yn, right? Because otherwise it would vanish at this point. It's of degree. Pardon me? Yes. Linear affine, yeah. Yes. So it's necessarily monic in yn, but then we have to add this smaller degree term, but it will spoil nothing. Yeah. So f less than d does not spoil the term yn to the power d. So this lemma is proved.
By the way, about rescaling, we said that after rescaling, this function in a equal to 1.
Yes.
Equal to 1. But what do you mean on rescaling?
I don't know. No, it's up to you. You can rescale A or you can scale F. It doesn't matter. It doesn't matter. Yeah. So why was I interested in monic polynomials? That's because of finite, maybe type modules. So we have an algebra A, and we have its module M. So it's called finite type. If it is finitely generated. So you can take A to some power capital N, and it will surject onto this module M. Okay, and in particular, you may have a morphism of algebras like this, and then B acquires a structure of a module. Here it is surjective, yes. It means it's finally generated. Okay, so the unit in some copy goes to the corresponding generator here. So B is an A module, namely, say if it's called phi, A acting on B is phi of A just multiplied by B. Okay? B is also an algebra, yes. And then it's called a finite A algebra if this module is of finite type. Okay, and the basic example of this situation is related to monic polynomials. So we take B is the polynomial algebra of in one variable modular some polynomial P of t, where P of t is monic polynomial. Okay. So then B is finite. And this is clear, I hope, yeah? And anyway, I think you know this in advance. Pardon me?
Why do we need the B from T being monic?
But how do you prove it? You use the most natural basis just of monomials. Okay, and then t to the power d can be expressed from all the previous ones, and then you multiply by t and you can express the next one as well. But if you would have some coefficient here and it's non-invertible, then this would not work. Okay, and also they sometimes say that T is integral over A. Okay. Here, yeah, they're K algebras or just rings. Yeah. Modules are like M or N or K or L, and rings are like A, B, or C. Then in your home assignment, you will have a problem to deduce from this the most standard formulation of M-Noether normalization lemma. Pardon me? It's just a terminology. I don't know. Still, you have such an element in B, right? I have a subalgebra A in this algebra B, and there is a terminology that says an element is integral over subalgebra if it satisfies a monic polynomial equation with coefficients of this subalgebra. Okay? It's just the terminology. Usually when you speak of modules, you say finite type module. When you speak of algebras, you say finite algebra. B is a finite A algebra. No, for example, the polynomial algebra is finitely generated over K, but I need not finitely generated, but finite.
Обычно, вот когда K отрицательные цены, говорят, что это морфизм конечного типа колец.
Yes, but I don't need. So far, I'm not speaking of finitely generated algebras. I'm speaking of finite algebras. There are various notions, but now I'm concerned with finite algebras. Okay, so I take algebra A. It's finitely generated. K algebra. And then the lemma says that there exists an embedding K of x1 and so on, xn into A, such that A is a finite K of x1 and so on, xn algebra. Okay, and you will prove it in your home assignment. It's an immediate corollary of this basic M-Noether lemma. And let me only say what does it mean geometrically. So suppose A has no nilpotence. So there's a notion of spectrum of A, that's a fine algebraic variety, and there is a map from this fine algebraic variety to the spectrum of polynomial algebra, in other words to the affine space and dimensional affine space, but this must be a finite morphism. So we didn't have a definition of finite morphisms yet. We will speak about them more, but it means that it's surjective and all the fibers are finite. Okay, and you will also prove this in your home assignment. somehow you know that any algebraic variety is embedded into a fine space, right? Pardon me?
В домашнем листочке нельзя было этим пользоваться. Каждый многообразие может быть вложено.
Oh yes, absolutely. That's by definition, because you know that A is finely generated. It means that there is a surjection from maybe Z1, so Z capital N, onto A, and this means that A is embedded into some big affine space like this. Okay, but I claim that there is a projection to some smaller affine space here, such that so it's not A, it's the spectrum of A. That the induced map is finite. Okay, and you see, we already proved this basic lemma. It's easy to deduce the familiar, well, the common statement of noted normalization lemma from this, but it's a very powerful statement. We'll use it now to deduce Hilbert-Null-Stellensatz, but it's all used all over algebraic geometry. For example, it immediately implies that any smooth algebraic variety is étale locally equivalent to just a fine space, and this is used all over the algebraic geometry. So it's a very, very basic statement. Nothing. The dimension, well, this dimension is the same as dimension of A. We will speak about dimension next time. But any point, any smooth point of an algebraic variety is étale locally equivalent to a smooth point to any point here. We will discuss this later. Okay, so now let's go to Null-Stellensatz. Oh hell, I will not even prove it today. Okay, so I will have a polynomial algebra like A, and I will have a module over it, and it's a finitely generated module. Finite type module, and the theorem says that for any linear form U, that is U1 x1 plus so on plus UN xn, there is a polynomial, the monic polynomial, Q, such that, just in one variable, such that Q of U maybe M over Q of U M is not zero. Okay, or in other words, U of U from M to itself is not onto. Okay, and maybe this is part 1, and part 2 is that Q can be chosen linear. So Q of U is just U plus some constant C. Okay, and so 1 immediately implies 2, right? Because we are over algebraically closed field, so any polynomial is a product of linear factors. U plus C1, U plus C, K, no K, but okay, CL, and since this product is not onto, then at least one of the factors must be not onto, right? Okay. Now, what does it have to do with Nullstellensatz? Maybe corollary. That there is a point A in our affine space such that M modulo the corresponding maximal ideal is not 0. Okay, this is really closer to the Nullstellensatz, and the proof is immediate from here, because start with take U equals x1, and then x1 minus a1 M is not M. Okay, then take this quotient M modulo x1 minus a1 M, and apply to it again the same argument. Take U equals x2. Find A2 such that well, find A2 such that M modulo x1 minus a1 modulo x2 minus a2, and this is M modulo x1 minus a1 plus x2 minus a2, and this is not 0, and so on. And finally, we get that M modulo the sum of xi minus ai is not 0. And this is just our maximal ideal. Okay? So we prove this, and now let's prove literally Nullstellensatz.
В плане суммы идеалов.
Yeah. Mm-hmm. We take an ideal. Here, yeah, fine, and here also, yeah. An ideal, a proper ideal. So it's not the whole ring. Then there is a point A such that all the elements of this ideal vanish at this point. Okay, and the proof is immediate. Let's take M, the quotient, or model of this ideal. Okay. Then we know that there is such a maximal ideal that this quotient is not zero. But this means that the quotient of K of the polynomial algebra modulo J plus this maximal ideal is not zero. But since MA is a maximal ideal, this necessarily means that MA contains J. Contains J. And that's what I wanted to prove. Okay? And note that this proof never used Max-Zorn lemma, for example, anything like this. Yeah, we didn't yet prove this theorem, but modulo this theorem, it's very elementary. And the proof of theorem is also very elementary, but unfortunately I am very slow and we have to stop now. So in your home assignment you will have this Eminem-Noether lemma and things like this, and if you want you may use this theorem. You don't really need to use it as far as I understand, but you are allowed to use it, and we'll prove it next time. So sorry for being so slow. Yes.
Я не понял про или конечного типа. У нас конечная порожденная пропуска.
Let me stop.